This lesson is 10-3, and we're going to take a look at continuity. Now, continuity is an important aspect of math, especially because when it applies to functions, we need to know if that function is going to be continuous, or at least what intervals are going to be continuous. Now, why do we want to know that? Because if those intervals are continuous, certain properties will apply to them. And so as we learn about functions and we learn new mathematical techniques, we have to know how to describe. We need to know how to find certain elements. And being able to find those certain elements, well, to find them, we'd have to know if it's going to be continuous. So we're going to focus on this definition of continuity, and we're also going to focus on the different types of discontinuity. So let's start with that definition. Mathematically, a function is said to be continuous at x equals a if these three things apply. The first, the limit as x approaches that number of your function exists. Meaning, when you plug it in, it's true. Now remember, when we were looking at a few functions, when we plugged in the limit, we got 0 over 0, or we got a value over 0. Well, that would mean that they did not exist necessarily, but know that it would first have to exist. So we have to make sure that the limit exists. The second piece, this is where it covers that 0 over 0. The f of a has to exist. So we first find, does the limit exist at that value? Well, now we have those holes, or the point discontinuities. Well, now once we know that f of a also exists, well, then we know that that eliminates the possibility of a point discontinuity. And then we have to take the limit as x goes to a of that function. It needs to equal the same value as if I just plugged it in. And it's kind of like taking that last little element and kind of tying both of them together. So you check off that this exists, you check off that this exists, and then you make sure that both of them equal each other. And if you can determine that, then we know that the function is continuous at that given value. So now that we know what is continuous, now we have to look at the types of discontinuity. The first is called a point discontinuity, and that is at an instantaneous value in which there is no defined value. The rest is defined except at that given point, which is why we call it a point discontinuity. Now, the limit may necessarily exist, but that value at f of c does not necessarily equal it. Right? So the value of f of c does not equal the value for that limit, because the value for the limit is here, even though the value for f of c is there. So that third condition is not met, so therefore that's why we can say it's discontinuity or discontinuous. The second is going to be an infinite discontinuity, and the way that we recognize this, it's typically asymptotic, and it goes on to infinity, right? So we know that we can describe it as an infinite discontinuity. And the reason why that we would say that this is discontinuous is because the limit as x approaches that value, it's infinity or negative infinity, so the limit itself does not exist. The last type of discontinuity is going to be the jump discontinuity, and typically you see this when we have two separate functions, so this would be like function 1 and this would be function 2, and it's almost as if it jumps to that next function, and so they look almost different. Now, the reason why we would say that this is discontinuous is because when you take the limit as you approach from this side, and you take the limit as you approach from this side, well, it doesn't exist. So therefore, the limit itself doesn't exist. There's our contradiction, and so therefore that's why that is discontinuous. So let's first examine this problem here, x cubed minus x squared minus 17x minus 15 over x plus 3. And it's asking us what intervals is our function continuous. And so I know that due to my domain, I want to have level of restriction here. So I set that equal to 0, say it can't equal that, And so the value that would make me divide by 0 is going to be -3. That right there, I don't know if it's necessarily a point discontinuity or if it's an infinite discontinuity just yet. You'd have to graph it to kind of verify that, or at least plug in some values and see what's going on. Maybe the top it factors and something will cancel out. It's irrelevant right now. All I know is that it's going to be discontinuous. And so if it's asking me for the values that are continuous, that means that if this is that hypothetical x value that's discontinuous, it's going to be continuous on either side. So that's going to be from -infinity to -3, and then from -3 to +infinity. So the only value that causes it to be discontinuous is that -3, but everything else is going to be continuous. So let's examine what type of discontinuity is exhibited by this function here. So for us to do that, it's nice to see maybe if something reduces, or at least let's check to see what the domain is, because once we know the given values themselves, it's going to help us. So I take the denominator, I factored everything, set it equal to 0, and I know that x can't equal -3 and +3. So I'm going to take the limit of each individual one. If I take the limit as x goes to -3 of my function, and as x goes to +3 of my function, and let's see what happens. Now notice if I go to -3, I get this 0 over 0. Well, we learned that that is a removable discontinuity, like, right? It can be removed, and it's going to be that instantaneous point in which it's going to be discontinuous. Because it cancels out, I do get this -1 over 6. I can conclude that that is going to be a point discontinuity. This last one, this as x goes to 3, I get an undefined value. Now we kind of learned, and maybe even previous lessons, like when we took a look at rational functions, that represents actually a vertical asymptote. And so when we see a vertical asymptote, that implies an infinite discontinuity. And so that's this value here is going to represent the discontinuity, or an infinite discontinuity. The last thing is sometimes we want to use algebra to be able to make our functions continuous. Because if we know that the function's continuous, like I said, these are the three things that we want to make sure is true. And if they are true, then therefore we want to make sure that the function's continuous. And if it's continuous, then it has certain properties. And so in this instance, it says find the value of k that makes our function continuous. And so what I want to do now is I want to make sure that, well, the limit as it approaches that value, sure, it's a square root, so that should work. Looks quadratic, so that should work. F of a exists, okay, so I can plug in that value there, sure, that's great, so that's going to work. Now I have to make sure that these two are equal. So to make sure that these two are equal, what I'm going to do is I'm going to have to then take my two values and I'm going to set them equal to each other. Now remember, because this, for my piecewise function, is where it's going to break my function apart, right? So meaning it could either be that jump discontinuity, or at this value I want to make sure that they're connected. And so I'm going to plug this 2 in for my x on both of these, because that's what we're looking at. We're looking at the value of x equals 2 because this is the issue. That's where it could either jump or it's actually going to be connected. And so I plugged in 2 in for x on for this function, plugged in 2 for x in this function, and we want them to be equal to each other, because if they equal each other, then we know that they're continuous. So from there, all I need to do is solve for k. Simplify this, that became square root 11, that became 2. Subtract 2 on both sides, enter that in your calculator, and you get k is approximately 1.3166. And so right there, that is the value of k that's going to make it continuous. And you can even verify this on your calculator. You can plug this in, and you can plug this in and check out at x equals 2, and you actually should find a value that's then going to make it continuous. It won't say undefined, it's going to connect perfectly. To conclude this lesson, what was continuity that we went over in our lesson? Well, we said that 3 things have to be true. The first, as x approaches a certain number of our function, the limit of that has to exist. The second was the value at that function has to exist. And then the third, they both have to equal each other. Now, what types of discontinuity are there? The first is a point discontinuity. And so that's going to be this scenario here where there's an instantaneous blip in which, or a point in which it's discontinuous, but the rest is going to be continuous. The infinite discontinuity where it approaches infinity. And then the jump discontinuity where it looks like it jumps. Now, the reason why these have to be, all 3 of these have to exist is because it accounts for all 3 of these types of discontinuity. Now, this does conclude our lesson. If you have any other questions, please leave them in the comments.